we had, we're going to start with just looking at the graph of sine x and try to figure out what the derivative for that would be just by looking at the graph. So if I do that, I notice like, well, kind of everywhere where, goodness, come on here now. Everywhere where the graph hits a maximum or a minimum, well, the tangent line there is horizontal, so the derivative should be 0. And here it looks like the is the steepest downward part, and it looks like the slope there is about -1. And here, like the steepest upward part looks like the slope's about +1. And it turns out like this matches up pretty well with the graph of cosine. And this is something we did in a homework problem, I think, back in chapter 2 somewhere, right? So prospectively, it looks like the derivative of sine is cosine. How would we prove that, though? Nope. How have we proved all these derivative rules up until this point? The limit definition of a derivative. So the limit as h approaches 0 of sine of x plus h minus sine x over h. Yes, Nolan?
So is cosine the derivative of sine?
That's what we're saying. That's what we're trying to prove, yes. So d dx of sine should be cosine. All right. So this is a familiar limit definition of a derivative. Somehow we have to get that h in the denominator to cancel out or something, because we can't do a direct substitution while it's still sitting there. Any ideas? So you'd get sine squared x plus h minus sine squared x. What's that going to get for us? Not much, but not a terrible idea. That's something we've done before, and that does look a bit like a conjugate.
Add in two things that like add together to make 0.
Okay, another thing we've done before, but turns out not what we're going to want to do in this case, because there's not some factoring that we're going to be able to do by doing that.
So then the sine x plus sine.
Oh, no. We can't distribute trig functions.
Yeah.
What can we do with that, though? There is an identity. The angle sum identity for sine. Anybody remember? It's okay. It was a long time ago. It is like sine alpha times cosine beta plus cosine alpha times sine beta. So sine x times cosine h plus sine h times cosine x minus sine x. Now, why is that an improvement?
Because you can factor out sine.
Well, it gets the x and h separated, right? At least it gets it out of being inside of the same trig function. Now I have trig functions with x's and trig functions with h's. That's going to be an improvement for us, right? What we want to notice now is, okay, well, I see two pieces at least where I have a sine x. What I'm going to do is I'm going to group this into two separate fractions. One fraction is going to have the sine x's in it, and one fraction won't. We'll write them with a common denominator of h. And now let's go ahead and do a little factor. So I'm going to factor off that sine x, and then I'm going to use a limit law to write that as like the product of two limits. Cosine. And I'm going to do the same kind of thing over here with this other piece. So I'm going to take the cosine x, the part with the x in it, and separate it out. Now, why would I want to separate off the parts with the x's on them, like what I'm doing here? Yeah, so if I take the limit with respect to h of something with no h's in it, the limit just goes away, right? So if we look at this, the limit as h approaches 0 of sine x is just sine x. The limit as h approaches 0 of cosine x is just cosine x. So we have that part done, right? Anybody recognize this? Let's see, where are you? There it was. Way back in 2.2, we observed that the limit as x approaches 0 of sine x over x is 1. Everybody okay there? Okay, so I'm going to use that. Where was I here? So that's 1. Now, what should this limit then be if this derivative needs to come out to be cosine? It's got to be 0, right? Let's see if we can get that limit to come out to be 0. If we do, then our proof is basically done, right? Because we've got what we needed. Now, Nolan, your idea of multiplying by a conjugate, this feels like a much better idea. Here, why is that going to be a good idea? What am I going to get when I multiply by the conjugate?
Cosine squared h minus 1. That's sine.
Close.
Sine squared.
Closer.
Is it tangent squared?
Nope. You were closer before. Well, I know 1 minus cosine squared is sine squared. So that's negative sine squared, yeah. Are you going, at this point, Mr. Kulik, I have to remember these trig identities? What's my answer going to be?
No.
Wrong. Yes. Yeah, we do have to have those still. Oops, that's supposed to be plus 1. Sorry. Okay. All right. So if I look at this now, I'm going to separate this into 2 chunks. So what are we going to do? We're going to have a negative, well, let's just do our sine h over h. And this we know is 1. And over here we can do a direct substitution, right? What's sine of 0?
0.
And cosine of 0?
1.
So I have 1 times 0 over 2. What's that all equal out to?
0.
Yes! That's what we needed it to have happen. So we get cosine and we're done. Would I expect you to do a proof like this on a test?
No.
No. Why are we doing it in class?
Because something true.
Because you'll probably, in your college calculus course, have a professor that just wants you to prove things. And we should at least have some practice witnessing what that kind of process looks like, right? All right. So things we picked up from doing this. The limit is theta approaches 0 if sine theta over theta is 1. The limit as theta approaches 0 of cosine theta minus 1 over theta is 0. And then the derivative of sine is cosine. So those were the 3 pieces that we kind of like, or the 2 pieces we needed to end up with that derivative rule result. Let's do an example. Here we're said to differentiate y equals x squared times sine x. How am I going to do that?
Use the product rule.
Excellent. So Nolan's identified that there's a product rule here. We have x squared times sine x. And algebraically, is there a way for me to combine the x's in here to avoid a product rule?
Probably.
Definitely not, right? You can't multiply something outside of a sine with something inside of a sine. That's no bueno there, right? So our derivative is going to be x squared times the derivative of sine x plus sine x times the derivative of x squared. What's the derivative of sine x?
Cosine x.
Cosine x. And the derivative of x squared?
2x.
I'm going to put the 2x out front because it feels like that's the more natural place to put it. Can I do anything more? Nope. That would be my final answer. What do you guys think? No big deal there, right? So we know the derivative of cosine is sine. I'm sorry, other way around. The derivative of sine is cosine. The natural next question is, what's the derivative of cosine? Well, the derivative of cosine is going to be negative sine. How would I prove that?
What? The same way you just did.
The same way we just did. So we just, again, set up the limit definition, but we're going to skip the doing of the actual proof here. Works very much like the previous one. You do the exact same steps. You use your angle sum identity to rewrite cosine of x plus h. You factor the cosine x's, break it apart. You're left with the same 2 limits that you had before that are 0 and 1 respectively. Everything cancels out, blah, blah, blah. The next identity we have is the derivative of tangent is secant squared. How are we going to prove this one? Sure we can. This one we're going to do. And guess what we're not going to use? I'm not going to use a limit to do this. Could I?
Yeah.
Yeah. Is it going to be ugly? Yeah. Instead, what I'm going to do is I'm going to think about tangent as
Sine plus cosine.
Sine over cosine. So if I want to take the derivative of sine over cosine, what would I need to do?
Use the divide. What's it?
Quotient rule?
Quotient.
Yeah, so we're just going to use the quotient rule for a derivative. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. The derivative of sine is cosine. And derivative of cosine is negative sine. Cosine squared plus sine squared is? Nope. 1. There you go. So we have 1 over cosine squared, which is secant squared. And we're done. That was a little easier than doing a limit there, right? Now, we could find the derivative rule for cosecant, secant, and cotangent using similar method, right? Just using the quotient rule a bunch of times for each of those. We're not going to do that here in class, but I'm going to summarize those identities here in this table. So this is all 6 of your trig identities, or I'm sorry, trig derivatives. Yikes. Do you have to memorize these?
Yes.
Yes. All right, let's do another example here. So this says f of x equals secant x over 1 plus tan x. It asks us to differentiate this and then find the values of x where the graph of f of x has a horizontal tangent. So to differentiate this, what am I going to have to use? Quotient rule. Great. After I've gotten the derivative, how do I find the values for x where the graph has a horizontal tangent? What is the slope of a horizontal line?
0.
So I'm going to set the derivative equal to 0 and solve for x. Everybody's good with that plan?
Yes.
Good. All right. Let's start with the derivative then. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That sounded bad. Okay, so let's do some derivatives now. What's the derivative of secant?
Secant x times tan x.
Secant x times tan x. And derivative of 1 plus tangent x, 0 plus secant squared x. Yuck, Mr. Kulik. How am I supposed to solve this thing equal to 0 now that the derivatives are done? Well, we got to do some cleanup, right? Ideally, what I want is that numerator to not be the difference of two things. I want that to be a factoring, like just a bunch of things multiplied together. So let's look at what we can do there. Well, I see that both pieces contain a factor of secant x. So let's start there. I can then multiply this tangent through. So let's write it this way. And then I got to make sure this negative sign gets distributed through. That's looking a little better there, but I don't like this tan x plus tangent squared minus secant squared part. I'd like to do a little bit better there. What can I do with that? I could, but what else can I do with secant squared? I could turn it 1 over cosine squared. Yeah. By the way, cosine squared, not just 1 over cosine.
Oh, is it 1 minus tan?
It is one of the Pythagoreans for sure, right?
1 minus tangent squared plus 1.
So it is secant squared is tangent squared plus 1. And you're going to me right now, Mr. Kulik, I have to memorize these too? Well, here's what I would tell you. Do you know sine squared plus cosine squared is 1? Yeah. How do I get P3? I just divide this by cosine squared. That's tangent squared. This by cosine squared, that's 1. And this by cosine squared, that's secant squared. So all I really expect you to do is have the first one memorized, which you already do, and realize that to get the other ones, I just divide by sine squared or cosine squared, which I think is probably reasonable. Okay, so if I do that, if I substitute secant squared for 1 plus tangent squared, I got to make sure I distribute that negative sign through the whole thing. But if I do that, some nice stuff starts to happen. And now I'm left with just a single trig function in that other factor, right? And now I feel good about setting that equal to 0 and starting to solve. So far, so good. How do I solve this equal to 0? I got a fraction that's equal to 0. When is a fraction equal to 0? When the numerator is 0, right? Except what other time? When the denominator is also 0, right? So whatever answers we find here, we're going to have to check to make sure we don't get a 0 denominator from them. But on inspection, it's going to be pretty clear that our solution from tan x minus 1 isn't going to give us a 0 denominator. So the only possibility will be from the secant x solution. And you'll see that that turns out to not even be a big problem. Okay, from here, what do I do? Yeah, so I can apply the zero product property. So I have two things that are multiplying to give me 0. So I can just separate those two factors and set them each equal to 0. What's the solution to secant x equal to 0? Okay, so you can say 1 over cosine x is equal to 0. So if you do the reciprocal to both sides, that's the same thing as saying cosine x equals undefined. Does that happen? So what's our answer? No solution for that. Oh, that's good, because that was the part that could have possibly given us the extraneous solution anyways. That's nice. If you remember the graph of secant, does it look like it's, like this? There's no x-intercepts on it. So, anyways, that's good. How am I going to solve tangent x minus 1 equal to 0?
Tan x equal to 1.
Okay, add the 1 over. Anybody remember where tangent is equal to 1? Nope, that's going to be negative 1. 45 degrees, right?
Yeah.
45 degrees, which is pi over 4. And
Plus 2 pi.
Not plus 2 pi.
Oh, is it plus pi?
It is pi k. Yeah, why is it pi k instead of 2 pi k?
There's 2 spots.
Well, it's because the fundamental period for tangent is pi instead of 2 pi. Remember, for sine and cosine, the fundamental period is 2 pi. For tangent, it's 1 pi. So there's our answer. Well, this was our derivative, right? That's our best simplified derivative. And then those are the x values where we have a 0 slope. Or the tangent line would have a 0 slope, I should say. So far, so good? That was a little bit of work there. A lot of trig, right? Okay. Let's look at our next example. An object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t equals 0. Its position at time t is given by s of t equals s equals f of t, which is 4 cosine t. Find the velocity and acceleration at time t, and then use them to analyze the motion of the object. So what is the relation? How do I find the velocity?
It's the derivative of that.
It's the first derivative of position. So the derivative of 4 cosine t is going to be what?
4 negative sine t. Negative 4 sine.
Yeah, so I'm going to raise negative 4 sine t. 4 times negative sine t is just negative 4 sine t. Everybody's okay with that? How do I find acceleration?
The derivative of negative 4 sine t.
Yeah, it's the second derivative of position. Okay, and what is that going to be?
Negative 4 cosine t.
Good. So far, so good. Okay, and then it says use them to analyze the motion of the object. Okay. Well, let's start by just kind of figuring out what the maximum velocities and accelerations are going to be. What will the maximum velocity be?
Or 4.
4. The minimum?
Negative 4.
Good. Acceleration max?
4.
And the minimum?
Negative 4.
Who has a question as to how Nolan came up with those so quickly? Everybody's okay? Great. What value of t would give me my maximum velocity? When is sine going to be equal to -1? Thank you. Very good. And it'll be equal to +1 at pi over 2. Good. All right. When is the maximum acceleration going to occur?
0.
Nope. That's going to be the minimum.
Pi, yeah.
Oops. You started saying pi as I was writing 0, and I just wrote pi. So let's look. So at t equals 0, my velocity should be 0, and my acceleration is -4. So that's initially, like we're at like no motion, right? We're at the bottom of the spring, but it's ready to like start whipping us back as hard as it can. At pi over 2, our velocity is -4, and the acceleration is 0. So at that point, like, I think we'd be passing by the rest position of the spring, like before you stretch the spring and let it go, like wherever it was just resting at, that's the position it would be at. And then it's going to be zooming back to like compressed as far as it can. All right, the next position is 3 pi over 4. There, the velocity is 0 again, but the acceleration is +4. So again, it's reached now the top, like the spring's compressed itself all the way back up, highest potential energy again, ready to pop back down. And then the last position is at pi. Here the velocity is at its maximum. It's zooming down, and the acceleration is now at 0 as it's starting to slow, as it's beginning to stretch now, right? Does that feel okay on what we did to analyze? We just kind of looked at the relative mins and maxes for those things since they were periodic. All right. Next question. Find the 27th derivative of cosine. Mr. Kulik, are you serious? Who thinks there's got to be a shortcut to doing this? There absolutely is going to be a shortcut to doing this. We're not taking 27 derivatives here. You're dreaming. Mr. Kulik loves math, but he's not that big of a masochist. All right, let's just kind of start taking derivatives until we see kind of what's going on here. So derivative of cosine is negative sine. Okay. So the second derivative will be the derivative of negative sine, which is negative cosine. And the third derivative of that is going to be positive sine. And the fourth derivative then is positive cosine. So what we're seeing is that every 4 derivatives gets us back to the beginning again, right? So I can say, okay, well, the 24th derivative should just be back to cosine, right? So the 27th derivative should be the same as the third derivative, which should be sine x. So we managed to do it with just 4 derivatives. This type of function is called a cyclic function, one that just like has a finite number of values and it just cycles back over itself over and over again, repeats itself. like the sine or cosine function, right? Oh yeah, some fun limits here. All right, limit as x approaches 0 of sine x over 4x. How am I going to do this? I can't do a direct substitution because what do I get? 0 over 0. Oh no. What does this kind of look like though? If you ask me, it looks a little bit like this guy, right? So what I'm going to want to do is I'm going to want to either try to write this as sine 7x over 7x or sine 4x over 4x. Which one is possible? One is possible, one is not. Excellent. Right, we can't get access to the stuff inside the sine, but it's pretty easy to get access to the 4 there, right? What would I need to multiply that by to cancel out the 4 and replace it with a 7? You mean 4 over 7?
Oh, yeah.
But I can't just multiply by that, so I just need to do it again by the reciprocal. Why am I doing that? Because it's now like doing nothing at all. I'm just multiplying by 1, right? But I can do that. And now write this as 7 over 4. Limit as x approaches 0 of sine 7x over 7x, which is going to be
0.
You mean 1? Or just 7/4. Right, because this limit is just 1. If we just let theta equal 7x. Nah. So far, so good? Let's do another one. So here we have the limit as x approaches 0 of x times cotangent x. Again, what happens if I do direct substitution?
1 over 0.
I get 0 times infinity, right? Or plus or minus infinity?
Yeah.
Indeterminate. So what are we going to do here to do this limit?
The product rule.
Nope, because we're not taking a derivative.
Oh.
We're trying to do a limit.
Switch cotangent to...
Yeah, cosine over sine? Yeah, let's do that. Great. Why is that helpful? Look what we have right there. That's almost what we need, right?
Yeah.
That's x over sine. What do we want it to be? Sine over x. So remind me again, what's the reciprocal of a reciprocal?
Same thing.
The same thing. So what I'm going to do is I'm going to write this as cosine x over the reciprocal of x over sine. So I'm doing like the reciprocal of the reciprocal. Then I can apply my limit law. And it's okay that I'm doing this because what's that denominator? And what's the numerator? And I'm done. Woo! It's always satisfying when they work out like that. And it's like, oh, that looked like it was going to be real brutal. And it's like, oh. Now, to come up with the reciprocal of the reciprocal as your trick would not have been obvious at first sight. Like, again, Mr. Kulik has the advantage of having read the textbook and have done like thousands of these kinds of problems before in his career. And it's like easy for me to see that. But it wouldn't have been if I got back in the time machine as a 17-year-old doing it for the first time. Like, that's not an easy thing to see right away. But it's one of those like, oh, okay, once I've seen that trick, I can probably use that again and recognize it. But coming up with it fresh on my own, that would have been a good pull, right? That's a mighty effort. That's it for 3-3. In large, what are we really just doing in 3-3? We just got some new derivative rules that we just need to practice using in combination, specifically with like the product and quotient rules, right? Yeah. Can I point out one other thing? Let's do one other quick little example here. Let me use a different color to start the example. So let's say we wanted to find the derivative of this. If you look at this as it's currently written, what are you going to have to do the derivative? I'm going to have to do a quotient rule, and then inside of my quotient rule, I'm going to have a product rule, right? That doesn't look like a lot of fun. Did you notice anything here glaring at you?
Differences, like the one plus sin x and the one minus.
Yeah, this looks like there's a difference of 2 squares going on top. If I FOIL that out, maybe there's a good trig identity that I can use to make this problem considerably simpler.
Would that be equal? I'm sorry, cosine squared?
So good. So 1 minus sine squared is cosine squared.
Okay.
Yep.
So that, can you simplify that?
Yep.
It's cosine.
Yep. So let's take the derivative of that, huh? That's a lot better than doing the quotient rule with a product inside of it, right? And then trying to simplify whatever you got left to end up just at negative sine x. So keep in mind, as you're kind of going through this section, your trig identities are your friends. They can often take a really yucky problem and turn it into something that's really trivially doable. The calculus is trivial if you're able to simplify it effectively. Imagine if I had asked then for the third derivative of this, and you didn't recognize that you could do some identities and get that down to just cosine. What a mess doing like the third derivative of that is versus the third derivative of cosine, which is, we did a second ago, and it takes 15 seconds. If you try to plow through that, taking the derivative 3 times, that's going to be a nightmare. So again, if it seems like it's too hard, stop, go back, look if there's some algebra that you can do to rearrange things to make life massively more convenient for you. This is going to be one of the most important calculus skills you can develop, is being able to look at the problem and go, that's a nightmare of a derivative the way that's currently written. How else can I think about that so that the calculus is easy? Use your algebra tools, combine like terms, rewrite things with fractional exponents, do a trig identity, find some way to make the derivative easier than the way it's currently written. The AP loves to give you problems that are a huge time suck if you don't recognize the shortcut, and are massively easier if you recognize oh yeah, if I just do this, I can eliminate having to do anything other than a power rule or anything other than one derivative rule. Or if you don't, you're stuck like plowing through, like product rules and chain rules and quotient rules. And we haven't even talked about the chain rule next or yet, but like, so just kind of keep that in mind as you're going. Look before you leap. Okay. 3-4 is going to be the next section. We'll start that next week. I would advise you before next week, if you don't have your derivative rules stone memorized, including the new ones that we just got today, would not be a poor use of time to spend, 10 minutes a day just working on memorizing product, quotient, power, constant, multiple, sum, difference, these trig rules. Have those derivative rules stone memorized, because we're going to start using them all in combination of one another when we get into the chain rule section, where you're going to have like quotient rules inside of chain rules, inside of product rules with trigs in there and exponentials and polynomial, and it's all going to be like mashed together. And this will be like maybe the hardest part of like doing derivatives effectively, is that you're going to have like a lot of stuff going on inside of one problem. But what'll make it a little bit easier to handle, especially a little easier to follow when we're going through examples and doing stuff in class, is if you have these rules on instant recall. So when I say, okay, we need to do, like the derivative of this is, you're like, yes, it is. I remember that. It'll make things go much quicker, and you won't feel like so much catch up as we're kind of talking through things in class, okay? This assignment that's written up here isn't due this Sunday because we haven't had a chance for you guys to ask questions. It'll be due the following Sunday. What's going to be due this Sunday? Nothing.
Yes. Sorry.
It's okay. You can share for that. Now, would I do this before next class?
Yeah.
Yeah, I would, because like next problem set's going to have 3 at least in there. So I wouldn't want to be behind on that, but it's not a rush. You don't have to have it in for Sunday. You can pick away at things, like go slow. You can leave some of it till Monday or whatever. Like, it's not the end of the world, but like, no rush. Nothing for me, anyways. It's all for you. You know what I mean? And this next test is going to come quick, just as an FYI. I know. But this section, or this set of stuff we're doing, is going to be super like symbol pushy. Like not a lot of theoretical. Like even the last section had a lot of like kind of theoretical, like you have to understand, differentiability and when things fail to be a derivative and all that kind of stuff. Here we're just talking about derivative rules for like this whole block of sections before the next test. So it's going to be a lot of like, find the derivative of this, find the derivative of this, find the derivative of this kind of questions. It'll be very symbol pushy. It'll feel more like math problems that you're used to, rather than like, here's a multiple choice question with a graph and it's like, okay. It'll feel less weird and more like, the math you're accustomed to. So if we look here, we have 3-3, we've done that. 3-4 is the big one. That's probably the most important section of this next test. Implicit differentiation can be tough. We'll go through that slowly and carefully. Derivatives of logs are just more derivative rules. And we see a neat potential shortcutting that we can do for some nasty derivatives using that. 3-7 is like story problems. I'm just going to do like a couple of examples. 3-8 I'm not even going to do. I wrote the title and then I read the section. I'm like, I don't want to do any of this. And then 3-10 is basically like writing tangent lines again. And then that's it. We're going to have a test. We'll probably do what next week? 3-4, 3-5, and 3-6. The week after, we'll probably do 3.7 and 3.10, so we'll be looking at a test. You know.
From Halloween.
Yeah, probably. And we're gonna switch up the multiple choice portion is gonna be on the is gonna be the calculator section. And the problems are gonna be in the no calculator section. So we're gonna trade things up.
Wait, I don't understand.
Yeah.
Oh, wait, I didn't understand. What's the difference for this test?
Well, instead of the multiple choice being in the no calculator section, I'm going to give you like the problems to work out as the no calculator, and the multiple choice problems you're going to get the calculator for. Because I have something to show you. Well, we can show you now, I guess. There's no reason not to. Watch this. Let's say that we want to find, let's go back. You guys are all going to be so upset. Go back here. So let's say that we wanted to find this derivative evaluated at, say, 7 pi over 6. So I'm going to type this into my calculator, into the y equals menu. So I'm going to do the fraction command. And now I don't have a secant button on my calculator, but I can write that just as 1 over cosine. So I've typed that in. I'm going to exit out of here. I'm going to press the math button and scroll down to the bottom and look for this n derive. What's that symbol notation starting to look like?
A derivative?
A derivative. So I'm going to say, okay, I'm going to differentiate with respect to x. The equation I want to use is the one I stored in y1. So I'm going to press the vars button and then the y vars. We're in function mode. I'll pick y1. And we said we wanted to do that at 7 pi over 6. That's what I get if I had plugged 7 pi over 6 into this. Pretty nice, right?
Yeah.
So anytime we're looking at a derivative at a point and you have access to your calculator, you're doing it on your calculator. The AP expects you to do that. They're going to give you problems that are horrific to do by hand, that they expect you to just type into your calculator and press enter. Hence why this particular test, the calculator is going to be in the multiple choice section, so I can give you some problems like that you have no business doing by hand, but you just need to be able to do with your calculator. Everybody's okay? And we'll show you how to do that again another time in class. You don't have to practice it right now. I just wanted to show you after you've all taken the test and had like a bunch of problems like that. It's like, wait a minute, I could have just plugged that in my calculator. Yeah, you could have. It's exciting though, right? I wouldn't have, there's a reason I didn't tell you about it, but till after the test was done. Because I didn't really want you doing it that way. But by and large, you guys did well on the last test. Scores were in. The curve was less than last time.
There was a curve.
Yeah.
Oh, okay.
Yeah, so like last time we said 80% of the max score was full credit. Here it was 85 is what I did this time.
Wait, if you're at 85%, you got 100.
I graded, so there's like 46 total points. I graded out of 85% of 46.
Oh.
So it was like 39 something or another. I kept all the decimal points.
Okay.
But that's what I did to construct to get your grades. Probably next time it'll be 90% of max points or something. So we're just going to keep like, yeah, cutting down the.
I'm liking this this 85% though.
You guys did, I mean, a lot of you guys didn't even need anything, like had A's with nothing, you know? Because if we're gonna do any kind of curve, there's nothing past 100%, right? If you get 110, it's just 100%. I'm not putting in over credit, you know what I'm saying? But, so yeah, I mean, that's kind of where we're at. So just as a heads up, we'll probably have 2 weeks of lessons before we're kind of approaching another test. So, yes, sir.
See my homework